Should we slowly start and people will join us on the way during? Yeah?
Yeah, let's do it. Yeah.
Okay, all right. So we're going to talk today about modeling and its importance in ocean plastic pollution tracking. We're going to have 3 15-minute presentation today. You can ask a specific question to this presentation after each of the 3 presentation. And after this, we will have some time for discussion, which I'll try to moderate as the best I can. So first of all, we're going to have Dr. René Garello. He will give us a brief introduction and how modeling interacts with other key data in the study of ocean plastic. Dr. Garello is a professor at IMT Atlantic in Brest, and he's also the former president of IEEE Ocean Engineering Society, amongst other prestigious appointments. So René, the floor is yours.
Okay, let me share the screen.
I will signal you 1 minute before 15, so you know when to wrap up.
Okay. Okay, that's my screen. So do you see the screen?
Yes.
Okay.
I'm just going to say something I forgot to mention, that you can ask your questions in the comments section, and then I will read them at the end of the presentation. So feel free to use that. And you can go, René.
Okay, thank you. So this is the session that talks about marine litter in terms of the modeling of the ocean circulation and the need this modeling to be in connection with other kind of observations and other kind of inputs. Not this way, this way. Okay. So that's basically what I will do. In this slide, I've added also the two other presentation title. Christophe Maes will present the pollution of seawaters, ocean modeling, and Thierry Huck, depends how you say it, the modeling of ocean plastic pollution and the sources of uncertainties. The discussion will be focused around 2 questions, and Christophe will introduce the questions later, so you can read that on the screen now. Mainly the scale of the motion needed for the dispersion and what kind of scenario for the sources, which are related to the 2 talks. Yes, plastic is here, and unfortunately it's here for a long time, and it's mainly due to us. Contrarily to what the fish thinks that the invasive species may be another fish. No, it's us. No, don't worry. We are the leaders in that. Christophe suggested to me to add this slide, which is coming from Thomas Maes, the same name but no relation, I guess. And Shades of Grey, Marine Litter Research Developments in Europe was the title of the paper. And it shows the research categories which are addressed at European level by the projects. And you see that the topics of modeling is at the bottom, I would say, and the monitoring is at the top. So coupling that together is also a good way to have those two communities. In the previous session, we saw that some communities are working on the same topic but not talking together. So that's also a way to really have one point that was addressed in the previous session was also the, for instance, the essential variables. How do you measure that? Or how do you monitor that? The monitoring community has to understand what is first an essential ocean variable. So it's not so simple. Don't read that, it's too small, but that's you can go to the paper and look at exactly what means each of the categories that were addressed by Thomas in this categorization. Okay, and that's the topic of my talk, is what is the link between monitoring and modeling of the sea surface. And basically from space, especially with the satellite and the sensors on satellite, you can measure many parameters, which are high-level parameters, like the sea surface temperature, for instance, the color of the ocean, the true color, the sea surface height, the salinity, etc. And with the synthetic aperture radar doing the imaging, radar imaging, you can address kind of second order parameters like winds, currents, waves, swell, etc. And those are related also to the circulation, so that you start to see a kind of a connection, of course. What are the challenges for monitoring plastic in the ocean? The first one is that from satellite, which I presented in the slide before, especially the radar, they don't see the plastic. So you have to find a way to see something that is related to the plastic, and from one of the sensors. You can try to add some information or have some information coming from the sources or the sensors. And drones are really promising because they fly, of course, much lower, and they can detect on a smaller scale as well. That's the counterpart, the extent of some patch of garbage, like this one, which is a very large one. And so they are reduced in a sense in terms of sensors to optical or hyperspectral. They very seldom have a radar on board, but could be used as well. The other one that I'm just browsing through, what I call telecom internet, is a way to use some other satellites. Not all the satellites orbiting the Earth are observing satellite. Some are telecom satellite, and they can get information from devices, sensors, let's say in situ sensors. That's another way of linking observing from one space to observing from another space. And in situ sensors, of course, again, they are locally distributed. And so how can we improve that? I come to that later. So the final one of these inputs, and it's last but not least, of course, is the circulation. So Christophe gave to me this slide about the fact that we can do the model of the circulation by using three main steps. Of course, they will be refined later, but evaluation of the surface currents from an original model or an original point of view, and then indicate the specific initial position of particles. And that's important because that's, in the beginning, all these particles are equal among them. Then you can put some more weight on some particles if you know that they are coming, or you're near a river or something like that. And then you can put the trajectory and let it go, in a sense, and let the model run. It's not as simple as I explained, of course. Tracking, once you have all this together, you have to track something, okay? But that's a tricky part, but because tracking can be deceiving somewhere. For instance, if you look at this Gary Larson cartoon, those two sharks, they were tracking for miles something that was red, indicating to them that it's very important. And finally, they find out that, well, it's not what they thought they would find. It's not human, it's just a ketchup bottle. It's red, of course. So what do we have? So we have a great amount of data. We have data from satellite, which is huge in terms of amount. We have data from in situ measurement. We have data from in between, that's a drone or planes. We have data from the modeling itself. We have also data which I didn't mention there, but data from citizen science, for instance, observation on the beaches, etc. So we have about actually 10 to the power of 18 or 20 or 21 or whatever, and it's petabytes of data that are available. So it's not anymore at the level of a human. So of course, everyone is talking about artificial intelligence, but what kind of best practice should we associate to artificial intelligence? On the one hand, we have the processing, which is now correctly understood, the machine learning, the deep learning, that we can have that calculation done and power enough, computer power enough to, or strong enough to process all this data. And in a sense, we are, all these observations are the real world associated to the measuring devices and the processing and etc. in order to produce some results in the end. That must be put in at the level of what we discussed on the previous session on Monday and also in the plenary on Friday, last Friday, about the platform. At one point, the platform gathering all the data, etc., must be associated to some kind of processing. What are the drivers for having artificial intelligence? First, it's the data. We have data, and as I said, it's a lot of data, and we see that in some instances, we are missing some data. That is, we need more data. We thought that we have too much data, and in fact, we have not enough data. That's a kind of a paradox, but so we need, again, more data, and we need also models. So, for instance, the models or the modeling of the ocean surface circulation must be improved, and that's one of the questions, what is the scale? So the smaller the scale is, the more data you have. So, but the smaller the scale is, the better the results could be. So there is a trade-off there, which will be addressed. And of course, you need powerful computers, actually parallel GPUs in parallel, GPU accelerators in parallel. All that must be that the three main part, but it must be completed by the fourth one, 3 + 1, and the fourth one is us. It's our brain, and in this case, it's you. Final slides, and so I will let the floor for the question. It's I put 3 links here, which I will copy in a chat later. We made a small video, and I would like this to be, it's motion design. It's kind of, it's not naive, but it's short and should be understood to be, and it should be distributed to be understood by everyone. So that's my my last slide, and I think I'm on time, so let's go for question, if any. Thank you.
Yes, you are perfectly on time. Thank you very much for this. We do have time for a few questions. The first one is from Christophe. Christophe, maybe you want to turn on your mic and ask your question.
Yeah, I just want to know if there's somebody in the audience that already have some experience with IE and the marine litter. Seems to be not.
Yeah, we don't have any.
So René, can you detail a little bit more? What is the expectation that you have from ocean modeling in terms of IE?
Okay, the modeling, for me, the modeling is an input at the same level as observation from satellite. That's at the same time, we have observation that we think are the real truth, the real data, but are only observation that are observing something that is related to some parameters. So it's exactly the same for the modeling. The modeling is coming from a theoretical point of view, and in the end can produce data at the same, in the same way, or not the same way, but at the same level as the observation are. So it's not one complementing the other. I think for me, the data coming from the modeling, of course, get some information from observations, but are also, in a sense, observations. It's kind of another paradigm for me. It's they are as real as the observation from devices. So it means that what I represented as being the processing from the artificial intelligence and the machine learning and the deep learning, that they are a source of information. So in the end, all these inputs produce some kind of information that then is put on a platform. And of course, the plastic is not only where the plastic is, but what kind of data is related to the plastic presence or not.
So you're basically saying that you're going to be using the model output as inputs for the artificial intelligence models, right? But like, how do we know if the physical models are representing correctly the reality of the dispersion of marine litter well enough that, you know, we're going to train the artificial intelligence with the level of preciseness that is needed for
Yeah, well, for me, as in any measurement, there are possibility of errors. So it's just a statistical point of view, which is, I am a statistician, so I looked at life as the probability of occurrence or something. So we can have a level of confidence in a model. Of course, we need then.
But how can you quantify this level of confidence if you don't have enough of observations? That's my question.
Well, then we have to confront or we have to compare what the model says and then what we go and what we get from observation, direct observation on the field. But in a sense, it's the same. For instance, when with a imaging radar, I measure the wind, or I give information on the wind. I am not measuring the wind. I'm measuring the sea surface roughness. From that, I have a model, which is what it is, and a model then it says, okay, the wind is so many meters per second, plus or minus something. So it's exactly the same approach. And I'm not, as far as I know, especially in the middle of the ocean, Atlantic or Pacific, I'm not going there to say, okay, I'm measuring the wind and I see if it is correct. No, I think
Well, we have moorings for this. You don't have to go.
Yes, I know, but that's the same principle.
Yes, I understand. All right, let's move on to the next question. We have a question from Thais Fonseca Resch. I'm very sorry about mispronouncing the name. He or she, I guess she, is asking, how would the integration with data collected by other methods, such as boat pumps, beach cleans, etc., work?
Okay, that is a peculiarity of the machine learning process, is that the data, they don't have to be let's say in the same unit. That we have to stop thinking in terms of data in a unit like meters per second or salinity, I mean, milligram per liter or whatever is the good measurement, and etc. It's the systems get all the data, but immediately or not, but transform that into some kind of information. So if I know that the wind is this speed and there is the presence of something else in the water, and if I know that there is a relationship, my example is not very good, of course, but if there is a relationship, then I have this information. And I can then say, or the machine can learn that if there is a presence of this wind speed and this presence of something, then it's a category per itself. And we have to have the machine learning that, of course, but then the processing power that we expect. And especially tomorrow there is a presentation by IBM, and I think they might talk about the quantum computing, for instance. If you have enough power in computing, you can see it's not exactly a correlation, but a relationship, I call it this way, the relationship between two parameters. And they don't need to be in some kind of comparable unit. So to answer the question more directly, the integration is the data collected should go to somewhere that's the part of the system that needs to be proactive. That once they are collected, they are sent to this platform, and then the machine knows how to interpret and process whatever the unit is.
Okay, so I think that's all the question we have. I have actually an extra one. So the idea behind machine learning, would it be because we have the physical models, so the machine learning would add resolution, or would it add, serve as predictors for future plastic displacement? Or because what do you get out of it that you won't get out of a Lagrangian model plugged into a physical model?
You will get, you can use that to improve the model, but the idea is what I was presenting anyway, the artificial intelligence, which is kind of something above the level of machine learning. Machine learning is just a tool. I mean, it's just statistics, more or less, is to get all the different parameters and present a solution to us. It's here for helping us, not for if we set it to predict something. This artificial intelligence will say, okay, with all the data I have, all the parameters and all the models I have, this is the expected output. And so to answer your question, you can also use the tools to improve your model by adding parts or where you have, if the resolution is not good enough, you can infer some possibility at a local level, but it's not the same kind of process I was talking about. It's a different kind of process. You can use some algorithm to improve the model, but the one I was presenting there is to be at a high level and give some hints on what could be happening if we have all these parameters correctly understood and processed by the machine. Don't know if I'm clear.
Yes, yes. We have a last minute question from Carla Elif. She's wondering about ground truthing in machine learning. Is it similar to the process used in remote sensing from marine leader?
More or less, yes, more or less. We need to have some, we need to teach the machine that there are some hidden information somewhere, and that hidden information can be found in looking at the data. So we have to give to the machine the way this information is produced, and ground truthing means that at one point we know that if we measure that from space, from somewhere else, from a remote location, and if we have really, we are on the data is code itself, and we have the real value, then of course there is a difference. So what is the difference? How can it be explained? And if we can explain that, if we can understand, that's the role of the scientists. If we have the sensor that is good enough, then we know this relationship, and then we can tell and teach the machine, okay, if you measure that, if you get information that the measurement is so and so, and if you input the relationship, then you have an information, and you can reverse the process and say, okay, because there is measurement somewhere, I know that this is the truth.
All right. Thank you very much, René, for your presentation and enlightening answers to questions. We will move on to the next presentation from Christophe Maes. It will present the modeling of ocean pollution, and more specifically the scales of motions needed to represent floating dispersion. Christophe is a researcher at the French Institute of Research and Development called IRD, and he is based at the Laboratory for Ocean Physics and Satellite Remote Sensing in Brest. So Christophe, if you want to take over, exactly share your screen, and I will let you know when you're up by 1 minute.
Okay. Did you see my screen?
Yes, it's perfect.
Okay.
So once again, people who arrived a little bit later before my announcement, you can ask questions in the group chat, and then we'll go through them at the end of the presentation. And of course, after the 3 presentations, we will have 30 minutes or more to discuss in general ocean modeling. So yes, the floor is yours, Christophe.
Thank you, Audrey. So today we'll speak about ocean modeling with typical OGCM, general circulation models, and it will be only my point of view. We try to connect with other groups with using ocean modeling, like the group of Eric van Sibyl in Netherlands, but it seems that nobody was really could be present at the same time, so they have different projects and startup and kickoff for other projects, so it would be difficult to have everybody. So it will be basically only my point of view. And when we organize a session, we would like to discuss and try to prove to get some improvement about 2 main questions. So the first one would be what are the scale of motion in our model that we need for the floating dispersion of plastics or anything like marine litter at the surface of the ocean, principally at the surface of the ocean. And after it will It will be the second question about the estimation for the sources entering into the oceans. Because as you know, you can have any model, but if you don't put the good forcing of your model, you cannot expect to have the right response and the right solution at the end. And this part will be presented by Thierry just after myself. Just to be general at the beginning, I would just say that if we consider the plastics or even marine debris or anything else like a passive tracer, so we are facing a very old problem in physical oceanography. This is what we call the steering to mixing problem, and it's quite familiar if you're thinking about adding your cream to your coffee every morning. So it's a long time problem about the evolution of the tracer in the turbulent flows with a steering phase where you have the extension of the steering, the stretching of any particle that you put in your ocean model or in your ocean currents. And after, of course, when you are considering a parameter like temperature or a physical parameter, you will have some mixing when you are able to create some very high gradients. That is exactly what is shown on the little anime cartoon on your left. And as you can see, it's as Peter Muller and Chris Garrett says in the beginning of the 2001, that it's a very old problem and that needs to be parameterized in ocean model, especially because we are in a specific grid where you have some no resolution of all the movements of your ocean. But it remains challenging, especially if you are considering applied aspect. And I think that plastic is a really applied aspect of this problem. So today I will just speak about the steering part that is concerned depending on the resolution of your model. And it will be linked to the fact that we need to have the knowledge of our surface currents in the ocean. This point is really crucial. And it's not so easy to have exactly what is the surface current in the ocean. In fact, the good response to this problem is to understand the dynamics of the RC interface. But it's not exactly what we do actually, especially if you look at even at observations. So you have an example here of releasing of 3 types of surface buoys that has been done in the North Sea region. And the buoys is depending on the drag, where is the drag of your buoy. So for example, what is called iSphere is really a very surface buoy that is only dedicated for oil speed tracking, for example. Then you have the cod buoy that is a little buoy with a drift in plastics, which is representative at something like 1 meter, the first meter depth of the ocean. And then you have the SVP buoys. This is a surface velocity program, which has been done by the meteorological organization, I think 20 or 3 decades ago. And you can see that the displacements, even in a few short period of time, will be quite different depending on your level of the surface or the currents that you consider. So you can see that it's not easy to define always surface currents, but most of the studies are based on the SVP, and because the SVP could be associated with any drifting object, which has been put in place in the 80s, by the World Meteorological Organization, and the drag is fixed at 15 meter depth. So you can see that it's really a very nice data set that we have, depending now of if you consider drag or undrug, because if you remove the drag, of course, you can still have some measurements of the currents, or at least you can deduce the currents from the displacements of the buoy at the surface, but it's not representing exactly of the same product. The problem with that is that we have now very nice climatology of the mean seasonal cycle, because we have a lot of data and for many years. But if you look at the daily or near real-time observation, most of the times they are based only on the 1,000 or a little bit more than 1,000 active buoys, which means that we are able only to have some estimates of currents at 80% of the surface of the globe, and for typically square by 5 degrees by 5 degrees. And most of the buoys are also deployed in the subtropical and region, or at least the region between 60 north and 60 south. So it means that the variability of the large currents is relatively well depicted by the satellite altimetry, for example, but it leaves some important observation gaps for typical wavelength below than 200 kilometers and 15 days period. So it's why most of the time we go on model and we go on ocean model. And if you look before I show you some example with models for the large scale processes. So recently we review with under the auspice of Eric, what could be the physical processes implied for the marine dispersion. And you can see that we have identified a lot of processes where they are listed here on the right part. And after, the importance of each processes will depend in some way of the region that you are considering. So separately between the offshore, the continental shelf or the littoral, you would not have the same physics, which is really important for the different region. For example, if you look at the large-scale open ocean processes, you can see that, of course, you have some mesoscale that we don't know, and I forget to mention that the pink bar just indicates the incertitude that we have and the importance of the process, but when the line is thick, it means that the uncertainties are larger also. So for the large-scale open ocean, typically the offshore region, of course, we know that submesoscale will be important, mesoscale and submesoscale. The ocean stock drifts, so the effect of the winds and waves, small-scale process on waves, but which have an impact on the open ocean processes. The direct wind transport, when we consider a particular object, like typically plastic or like a bottle, it will be not the same if you consider a microplastic or a bottle of plastic, of course. And then the long mirror circulation, vertical, and so on and so on. And at the over part of the side, you can see that if you look at the littoral, you will have more information to complete with river plumes, for example, or constant dynamics, which is really driven by different processes. So in this group, in this work, which has been led by the SCORE working group called FLOTSAM, we also note that most of the studies which use, for example, the SVP buoys, have assumed a steady and non-changing ocean circulation model. And this is not exactly true. We know that we have some very important interannual variability, such as El Nino and so on, and climate change. And it will be important to consider these factors in the discussion, because if we convolute with the fact that the production of plastics is increasing with time, is not really constant. So we have to consider this together with the scenario and the sources. So let me show you, because I am more specialist for the open ocean processes, 3 different points, but some kind of key message or some kind of illustration I can give you about the importance of the time variability for the surface currents, for example, especially to address the long distance connectivity and pathway in oceans, in ocean basin, for example. And also why we need to consider high resolution horizontal currents, at least to be able to resolve the mesoscale activity. So the mesoscale are the eddy in the ocean, especially to estimate the time transfer on the specific pathway. So when we are able to identify some pathway, the time transfer will be very different depending on our ability to resolve the horizontal currents. And also why we need, I will finish with just one example of what we need to have more scenario for the sources. Basically also for the things, but it's really a subject that is not really too much work on this part of the problem. And it will be I will give the floor to Thierry. So what we try to do here, it's really what we call some kind of academic scenario, where we put at the beginning, at the initial time, one particle, one fictive particle, sorry, in the model. So we will, as René shown, with the currents, we will be able to reproduce the Lagrangian dispersion or the Lagrangian trajectory of the particle for each particle. So for example, here we put 1 million of fictive particles at the surface of the ocean with a 4-degree grid cell of the model. And you can see after 3 years, the dispersion, of course, the equatorial band is really dispersive. So we have a lot of divergence at the equator, and all this band is removing the particles. And you see after 10 years, you begin to see, or even at 5 years, you begin to see the convergence zones in the subtropical regions. What was interesting in this particular exercise, you can see that if you look at the last part, at the last year of the simulation, you have, of course, the 5 zones, which is known as the subtropical region of convergence. But you can see that for the South Indian Ocean, it seems to be connected with the South Pacific Oceans. And in fact, it seems that these two systems are not close. They can exchange some particles due to the fact that we have some eddies which are able to transport some particles between these two regions. And it has a very important consequence, because when we look at the time series, we just already see that it was possible that the South Indian Ocean is decreasing the concentration, so it's not exactly an accumulation zone, as we can see for the other one, which seems to be some kind of equilibrium after 10 or 15 years. So what we do is we look at the particle in the South Pacific Oceans, and we reverse the integration in time to look at where the particle was originally and then when they converge to the South Pacific Ocean. So you can see in 2004, the particles are in the South Pacific, and when you look back more and more in time, you can see that they're arriving for a lot of different places. Most of the time they are originating from the South Pacific Ocean, but you can see that some parts are arriving from the South Indian Ocean, and especially in the South convergence zone of the Indian Oceans. So it means that it's not linear in time. So you need to have a convergence in the South Indian Oceans before to have a transfer to the South Pacific Ocean. So you can see in this typical example that the long distance pathway really depends on the non-local and non-linear advection of the currents due to the mesoscale activity. We look at, here it's another example, and the connection between two islands. We are in the Coral Sea. You can see a little bit of Australia and Papua New Guinea on the map. And we try to connect the Solomon Islands with the Loyalty Island near New Caledonia. And you can see that we are able to do that with two kinds of models. We shown basically the same structure of the mean pathway between the two. But you can see that the time transfer for the fastened particle that we are able to identify in the model, which is shown in color in the upper part, it's only 52 days. But when you look at the resolution of the 4 degrees, it's 3 times more important in terms of connection time. So the time transfer between these two regions could be multiplied by 3 just due to the fact that we are not resolving the current at the same resolution. And we do exactly the same idea to look at the core of the accumulation zones, just to show that it was probably not a closed system, but also not a dead system, like not moving at all. This is very dynamic because the AD activity is as strong as any other part of the ocean world. And we look at some kind of geometry when we look at the source in the core zone. So this is the purple box in the middle. And we try to look if we can connect with the larger box representing here by the color bar around each region. So the first estimate that we do with the model at a 1/4 degree resolution, that we have no exit route. So it means that all the particle remains around the core zone. But when we look at the resolution at 112 or even a higher resolution, you can see that we are able to identify some connection between the core and the larger region. So it means that we are able to identify some exit route from the accumulation zones. So it was very interesting to show that, in fact, the resolution and the current structure will be able to transport or to transfer some particles from this region, especially. And what is that? Why is that? It means that it depends on the resolution and the fine structure of your currents. So here on the upper part, you can see this is a representation of the current, surface currents, but not in terms of amplitude. So it's not some typical arrows, but what is shown is only the direction of the current, the main direction of the current. And you can see that the color is showing when you look at the typical satellite currents based on altimetry and scatterometry, you have you can make we can recognize the big loop due to the circulation in the middle of the subtropical regions. But when you look at the very high resolution, for example, so basically you have the same idea, but the color is much more intricate between them. And in fact, it just represents what we call now striation. So this is a typical very fine structure of the currents, which is we are able to observe this now with altimetry, at least to have some idea about this striation. And you can see that in this case, the striation was a little green band that you see in the middle of the box, so going towards the coast. So just to finish and to make some sum up about what we learned about the surface dispersion at global scales. So we are able to identify some new pathways, especially for long distance connection between the interbasin, for example, in the conversion zones, which was due to the fact that we need to resolve the mesoscale activity in the ocean. We are able also to show that the systems are not closed, especially each system is not closed and is not because the particle is arriving that it will stay for a long time. You can have some exit routes between this core of the region of the subtropical towards the coastline, for example. And finally, I do not have time to discuss too much, but we have also tested some the different physical processes implied in the dispersion. That's especially when you add the Stokes drift, so the effect of the waves that could play a major role. So you have here an illustration of with Stokes drift and without Stokes drift. And you can see that, for example, the typical big influence will be in the Indian Ocean, where the conversion zones, at least the core of the conversion zones, could be displaced by 2,000 or 3,000 kilometers towards South Africa. This is quite a huge impact only by considering the effect of the waves. And finally, we try also to use our currents to test some different scenarios. So in the top here, you have the scenario with the academic scenario, where you put a particle everywhere. But when you put particle along the coast, and Thierry will come back on this, you can see that the finite solution is quite different. So it means that if you have to have the good response from your model, you have also to specify a good source at the beginning. All right, thank you.
All right, thank you, Christophe. Do we have any question from the audience, maybe? Feel free to turn on your mic and just ask directly your question to Christophe if you have one. Well, while people are thinking about their questions, I have one for you. Mm-hmm. You did not specify what size of particle. You keep saying particles, but like, are you taking the size or the mass or the volumic mass of the particle into account in your model?
No, in fact, yeah, that's a very good question, because in fact, we remain on the idea that the particle could be whatever you want. So it's just a particle, effective particle in the model. So, but you can associate some kind of mass or even volume or whatever you want. So it's remain free to the users.
So you don't have any effect of the wind drag onto your particles, correct?
Exactly. Yes. It's also, we want to do that because we want to stay at looking what are exactly the oceanic processes involved in the marine dispersion, and not to look at any specific product or even plastic, because in this case you have to specify a density, you have to specify a windage and so on. And of course you have to consider the winds. Yes.
Okay. And you don't have any, do you have any plans on integrating this or maybe a fragmentation?
Yeah, it could be an interesting scenario. Again, it's more a question for scenarios, in fact, but really the scales. But yes, you can imagine to represent the micro plastic with this particle, and after we can put some kind of parametrization in time, saying that after 10 years or 20 years, the fragmentation will transform this particle in terms of microplastics and so on. So it's possible to imagine any kind of scenario like that. Yeah.
All right, thank you. We have one question from Kalani Iakshani. Once again, I'm so sorry about this. In considering accumulation of plastic, what is the most important feature to be considered? Is it, is it meso or sub-mesoscale it is?
Yes, that's something that we want to test, and at this moment, the most important resolution that we use, it's only something like between 5 to 7 kilometers, but only for regional scales. So we do not have any idea about what will be at this scale the marine dispersion as the global scales. But it's too early to answer this question in terms of mesoscale versus sub-mesoscale, because sub-mesoscale will increase the variability of the currents, but probably also we realize that more complex pathway. So, and we don't know which kind of process will dominate. Does the amplitude of the currents will be more important than the complexity of the pathway? I do not know.
But for the accumulation problem, my point of view is that it's really a large-scale process associated with surface currents. And the question of mesoscale or sub-mesoscale activity is probably more linked to the dispersion processes than to the accumulation process, but that's just my opinion so far about what we've seen in the simulations.
Yeah, that's correct. But imagine that sub-mesoscale processes could be very important near the coast, or because we have more coastal dynamics, which is more complex most of the time. So it means that these processes will remove the particle towards the coast and not towards the accumulation zones. But the large scales of the accumulation zones are dominated by large scale processes. Yes, it's correct.
But maybe the sub-mesoscale could be important for fine scale accumulation at fronts or things like that. But I guess we don't really have either in observations, either like modeling results about this aspect.
Yes, correct.
All right, thank you. This is a very good transition to our next speaker, as well as the comment from Thais Fonseca Resch, who says the last graph is a very good visualization of the impact of plastic sources in the ocean. And I think Thierry has a very similar or the same graph, so we're gonna be able to see it again. So Thierry Huck here will be presenting the uncertainties in plastic sources for modeling ocean plastic pollution. And Thierry is a researcher at CNRS, which is the French National Research Institute. And he's based in the same lab as Christophe, who just spoke, the Laboratory of Ocean Physics and Satellite Remote Sensing in Brest, in France. So Thierry, if you want to put your presentation into full screen, and then we'll be ready to be listening to you.
Okay, so I don't know how to do that.
Yeah, me neither.
Oh,
at the bottom, next to
the bottom, and
you
hit
next to the minus.
Yeah, two more on the right.
To the right.
To the right.
Yes,
this one.
Okay. Okay. Since I don't see, okay, I couldn't test that. Okay, thank you. So what I just give a very brief overview of basically the uncertainties we face when we try to put realistic sources for plastics into our modeling experiments. So here, I just want to basically illustrate the complexity of the problem and to open up the following discussions. And at the end, I'll show some results that we have from our modeling efforts in this direction. So that was to follow on Christophe's talk. That was the difference we could observe with a very simple academic scenario where particles were initialized everywhere in the oceans, like pretty old experiments done by Maximenko and then to try to initialize particles only along the coast from linked to the density of population and river inputs. So we see that we have a quite large differences, not only in the total amount in the different conversion zones, but also on the distribution overall among the basins. So what are the main sources of plastic in the ocean? So there are at least 3 main sources, which are the input from rivers. And this has been summarized by Laurent Le Breton. And databases are available to document these different sources, basically. And that's what we use for our modeling exercises. So the major input from rivers are mostly in the around Asia, with the Ganges and the Yangtze, especially in China, but also like the Mississippi River in the US. There is the coastal population density input associated with the mismanagement of waste, and pollution can get directly from the places where litter is accumulated, and because of the winds and mismanagement, this can go directly as an input to the ocean. And here the major input are estimated from Hong Kong, Mumbai, Shanghai, but also like in New York City, for instance, in the major cities. And then there is a marine input directly from ships as along the major shipping routes, but also from fishing activities that are considered as the main contributor to the large pieces of plastic to the ocean. Okay, so for instance, this is a map of the mass of mismanaged plastic waste generated by coastal population in the different countries of the world. And this has been estimated by Jenna Jambeck and collaborators a few years ago. And here we have the largest input. The largest load is again in Asia, and we have mainly China contributing, and Indonesia and Philippines, Vietnam and Sri Lanka, and all these regions are expected to continue to be one of the main providers of plastic to the ocean for the following years. Okay. So if we have to have a kind of global map considering and comparing these different sources of plastic, well, we have on this map the fishing intensity is a large provider in terms of mass, because this provides mostly like big pieces like fishing nets and line ropes and etc. And we see this occurs already in the center of the ocean, especially in the West Pacific. We have the coastal input, which is linked not only to the coastal population, but also to the way waste is managed in these countries. And this makes big differences between large river. Okay, no, this is the population only, but you can have large population with a good waste management, but also like a smaller population with a very insufficient waste management. And then in blue, you have the river inputs that are particularly strong, like again, in the rivers I mentioned in Asia and in the Mississippi. I don't know if you see my pointer or not. Do you?
Yes, we do.
Yeah, okay, thanks.
Yes, it's okay.
Okay, and then there is the more general source from the shipping activities in the different, mainly along the major shipping routes. Okay, so the next thing, apart from the spatial distribution of waste input, we also need to take into account the temporal evolution of waste. This is mainly because the time, basically the time it takes for particles to go from coastal regions toward the centers of convergence zones is of the order of years to about 10 years. And what we see in modeling exercises is that it takes something like 10 years to get some kind of balance between the input and the kind of stable concentration of particles in the center of gyres. So within 10 years, basically, we see that the global plastic production has increased by something like 50%. So here it's the global plastic production as a function of time since the 1950s. And we see that this is almost doubling in less than 20 years, basically. And this is expected to continue over the next decades unless we have a real drastic solution to reduce the production. So once again, the plastic production is only a proxy of the amount of plastic that will go into the ocean, because this really depends on the waste management. And if with a good waste management, we could reduce a lot the amount of plastic that goes into the ocean. And basically we don't have really this is just an indicator, basically, and this is a socioeconomic indicator that I would call a proxy, but it's very difficult to get about what goes directly to the ocean, except monitoring, for instance, what is getting out of rivers. Okay. So also there is a large diversity of plastic sources, considering the size or the density. For what I know the best is only the floating part of plastics that we consider for now in our modeling exercises. We've not get into the study of all the plastic that gets directly to the bottom of the ocean because of its high density, higher than seawater. And there is this question of also the plastics who have densities close to the very close to the ocean density, and that really are not trapped at the surface and might travel at different depth. So in terms of macro plastics, we have all these fishing lines, all the containers, bottles, or tanks, or things like that. For the microplastic, we have the pellets, which is the way plastic is produced usually for industry, and then we have also all the small pieces that will result from the fragmentation of larger pieces, and this is not something that's something that eventually should be considered in the way we need to deal in the conversion between mass of plastic and number of plastics, as I will come to later. And then we have all the smaller plastics that are hardly measured in the oceans and that are linked to the fibers and to the smaller pieces than something like a third of a millimeter, and then all the nanoplastics that we don't know as well. And so I've looked at some. There are some estimation of the total plastic floating in the world ocean. This is a compilation by Marcus Eriksen and collaborators. And once again, they have considered the two ways of measuring the plastic. One is the counting of pieces, and the other is the weight. And if we look at the count and compare the count and the weight for the different size of plastics that we can measure with manta nets in the ocean experiments, in fact, we see that the largest count is in the small size, the plastic of small size, like between around 1 millimeter to 5 millimeter, which as considered are microplastics. And the largest weight is in fact in the plastics of larger size, and that are really the macro plastics. So we see right away that informations about the two ways of measuring plastic, the count and the weight, are important to track, because very likely the smaller plastics will have a large effect on biology, of the planktonic biology, whereas in terms of weight, this would be the larger parts, which first are more easily monitored by eventually satellites or imagery. But that accounts for the weight, but not for the number of pieces, basically. And then the question this raises is the appropriate way to model these plastics within models and to take into account all these different types of plastic. And right now, as Christophe answered to Audrey, is that for now we've just used plastic particles, and we've not associated to it some kinds of weights, which we could do, in fact, or and we've not considered different sizes of plastics and the eventual transfers between the different classes or types or size of plastics. Okay, so now in terms of the validation of modeling exercises with in situ measurements, in fact, once again we are facing this problem of looking at plastic counts or mass. And we are also facing another issue with the standardization of measurements at sea that have spanned a few decades, basically, within a world with increasing plastic. And we should, if we want to compare modeling results with observation, we need to take into account this, the time at which observation has been done, and also the wind conditions that were present when measurements were done, because the wind increases the vertical mixing of plastics in the upper water column, basically. So this exercise of standardization has been done by Eric Van Sebile with his collaborators, and we can compare on the lower left panel the raw measurements that has been taken at different time over 2 decades, basically, and the same in number on the top for standardized for, I don't remember which year was the reference, maybe 2010 or something like that, and the same standardized value, not in terms of mass, but in terms of, not in terms of number, but in terms of mass. Okay, so now these are some results that Fanny Chenilla is working on right now in our lab. Basically, she has compared 2 input scenarios, one associated with the reverse input as provided by Laurent Le Breton, and one associated with the coastal population, the coastal population on the right. And this is a product that is mixing coastal population and the mismanagement of waste. And this product is provided by Eric Van Sebile. So when we are looking at the sources, we see quite a lot of differences. First, the river input is extremely large in major Asian rivers in the Amazon, and it's really localized at some river mouths, basically, and the Gulf of Guinea also. And whereas the population input is much more widely spread with all along the American coast, North and South American, European and African coast. So let's say the input is much more spread along different coasts. So if we look at the total input from different regions of the world, we see that we have large differences at the basin scale, with something like almost twice as much input in the Northwest Pacific in the river scenarios and the population scenario, and some important differences in other regions. So out of this initial input, we conducted the Lagrangian analysis following this, so something like 5 million of particles representing these different inputs with the Ariane software, and using ocean surface currents from a global ocean reanalysis, the product at 1/12 of the degree provided by Mercator Ocean. And we are following these particles for 23 years and releasing particles every month for the 2 scenarios. And the results are quite different in terms of the concentration of plastic at the end of the simulation, that is after 23 years. We see large differences in the South Pacific, mostly with very little in the concentration in the river scenario because of very low input from the rivers in this area of the world, and much more in the population scenario. which is maybe more similar to closer to observations, to in-situ measurements. We see large differences also in the North Atlantic, again because of all this population input around the North Atlantic basin, and some differences in the South Pacific. Okay, so to come to the conclusions, what I would call a correct simulation of plastic concentration at the sea surface implies that we have correct inputs, the correct dynamics, and Christophe has detailed what we expect by that, and this is probably taking into account high resolution surface currents and Stokes drifts, eventually windage, depending on the type of particles we are considering, and correct removal or transfer processes like what we call beaching, or particle trapped at the coast, the biofouling that increases the density of particle from the surface that would sink with time, and the fragmentation. So I think at today we have large uncertainties on all these aspects, on specifically on the source scenario. I think the data that would be required for correct inputs are time series of river discharge in terms of plastic, a good spatial distribution of the population input, correct time variability, and distribution in size and density. And for all that, right now, we can't expect real data, but we need some kind of proxies built out of a few time series and a few spatial maps. Sorry. So I think one of the problems is that the validation of the input scenario is also complexified by the uncertainties in the other aspect, like the surface dynamics and the removal transfer, and the fact that for now we don't have that many measurements at sea, and it's not that easy to say that one simulation is better than the other. So I think on all this we need to progress, and this is the goal of the work in progress, I guess. Thank you very much.
Thank you for your presentation, Thierry. We have time for some questions for Thierry. If you want to unmute your mic and ask questions directly to him. Or, of course, type in the Zoom group chat if you want me to say your name in a very affluent way. I have a quick question for you, Thierry. Could you elaborate on those proxies? Like you were just saying that we won't, or we at least not have right now enough data to observe the actual amount of plastic in the runoffs of the different rivers. What proxies do you have in mind to be able to measure the variations of the inputs?
Okay, well, what I was basically thinking is I think that's what most people do right now, is if you want to, for instance, take into account the increase of the total plastic production, and so very likely the release at sea, you would multiply some kind of spatial pattern, which is the river input or the population input, or some mix of the three plus the marine input, by a total function of time. So basically, this is a simplification of the real world, because otherwise we would need like time series of each river mouth, and that's what I call proxy, some kind of a simplification of the problem, so it's tractable, and it's because we don't have all the data we need, that's for sure. So that was one of my idea, and I think it's very difficult to do otherwise right now.
Okay, but how would you take into account changes in policies that are done between countries? Like we've seen in the recent years that most of the European and American plastic garbage is sent to China, and now China a few years ago decided that they didn't want this garbage anymore, and it shifted towards Indonesia and Vietnam. Do you have any, because the numbers you're showing are from 2012, right? And I think that between 2012 and now, we've had a lot of policies that were into place, and how would you account for this?
Yeah, there must be some data sets available to see that in some river places, but first, I'm not aware of this, and probably there are some data but for sure not on the global scale. That's what I meant, that on the global scale, we can't really go into these details for now, because I had the impression that first, at least as a physical oceanographer, there is still some important work to do on the processes, and the input is probably as important, but for, let's say, I would let that to the socio-economic researcher, and more concentrate on the physical aspects. I think that, well, for instance, like the map that Christophe have shown on the effect of Stokes drift, basically we've seen a huge change in the large scale long time conversion pathways by including the Stokes drift. That was not, first, that I was not expecting, but second, that would not necessarily, but that would make quite an important difference apart from the input scenario. That's for sure.
Okay. So you're saying basically that the errors that are induced by the sources are somehow the same or smaller than the errors from the physical models in the ocean, the ocean physical models.
I'm not sure. Yeah, but, maybe it's going a bit too fast. I don't know. There has been some kind of modeling experiments with different sources made by Laurent Le Breton, I think, and with some kind of adjustment towards the in situ measurements, and given the difference in the scenarios, the final concentration were not looking like as different as I would have expected. But I know that the largest change I've seen so far was just putting Stokes drift into the physical processes, and there are probably many more to take.
But we are talking large scale, right? Because if you go at the regional scales, then you would have more differences, I would believe.
Yes, sure.
Okay.
Yeah.
So we have a question from Carla Elif. She's asking, what should be prioritized in subnational scale considering monitoring the sources of marine litter?
I'm not sure. I would need to think more at the question. The fact is, for now we've concentrated on the global scale, but at so subnational would be I understand the question as regional. Mm-hmm. It's not supranational. So at the regional scale, I'm sure. As for, we really didn't need a good data from river outputs. That's for sure, and from eventually from other sources that are very difficult to assess, like what is driven by the winds directly to the ocean or things like that. And I don't know if this kind of estimation has been done so far.
Okay, so Gilbert Atuga says, I agree with you, but we can't really go in detail on global scale, specifically in Africa, where there are lacks of data research on river mouths to inform the model. In short, the modeling is biased to developed countries due to the capacity to collect data. How this will be handled to give it a global acceptance as a challenge, How this will be handled to give it a global acceptance is a challenge. I'm not sure I understand the question. Do you?
Time part, at least.
Maybe Gilbert would want to turn his mic on and ask his question.
Okay, I think.
Thank you, Gilbert.
My question was a little bit general. When it comes to the issue of modeling, most of the time you'll find the data that has been used. If you look at the references, in most situations, it's based on developed nation data. It does not really capture developing countries in terms of data collection, which is actually lacking. So the model itself can not really be extrapolated to global scale. And if that has to be done, I don't know what is thinking about that in terms of the EASE model. Yeah, that's my question. Is it clear?
I'm sorry, I missed the point.
Yeah, I'm saying that in terms of the modeling perspective,
yes,
this was for the immediate presenter who actually has who finished presenting right away now. His modeling was really giving different scenarios of the input from population and river mouths and what have you, and he was really using references based on the paper. Actually, I've forgotten its name. The idea I'm talking about that the more if you are going to use that kind of information, then the modeling will be skewed towards developing countries, and it's really cannot be trained for developing nation. You cannot make a conclusion on a global scale using that modeling.
Well, the way I see it is that we are using data available, and okay, it's skewed towards developed countries for the accurate estimation of the input, and we have probably a larger uncertainty on the input of other countries. I guess for now we are a little bit at the beginning of this numerical experiments of plastic monitoring, and let's say probably within 10 years we can out of the results on the increasing measurements, probably we can have we can come back to the input estimation and see if there are problems in some estimation. That's the way I see it. I think right now we are a bit too far from this type of application. That would be, I don't know, some kind of data assimilation or something like that, or some other processes. But that's what they can do right now about like CO2 in the atmosphere. And so probably within 10 years, we can use the model to better estimate the sources and the location of the sources, and compare that with the data we have from the rivers and the population scenarios, or the input, basically. That's my point of view.
So basically to use the model in a reverse way. So like observing plastic in the middle of ocean and saying where it comes from.
Yeah.
With the models. Okay. Does that answer your question, Gilbert? Oh yes, sorry. Thanks for the answer. It's clear to me now. All right.
If I can make a comment, I had a question yesterday, I think, about the fact that the reporting could be biased because, for instance, if you look at the fishing nets, there is a money involved with reporting the fishing nets that are going over or not a boat. So someone make a comment about the fact that there could be some falsification in order to get money if you report something that doesn't exist. So I think that the comment from Gilbert was about it's not falsification, but it's this kind of what could be in a sense called a ground truth, which is wrong. It's not true anymore. So reversing the model in order to get an estimate and saying, okay, the estimation is better than any published ground truth is the way that I see this input data could be more valuable for what I was explaining before, this artificial intelligence system and so on. So there is a kind of a trade-off in improving the model with wrong data or missing data, or complementing the data by the model. That was a very good question.
All right, so should we just switch to a general discussion around modeling in marine litter? Yeah. So once again, if people want to, oh, sorry, I'm looking at the questions. Okay, if people want to, you know, say something, just turn on your mic and yes. So François Galgani has a comment. Please turn on your mic. Make that
yes, normally you listen to me normally. It's okay?
Yes, go ahead.
Okay, thank you. So I have a question. I mean, actually, we are compiling all the data to prepare the World Ocean Assessment for United Nations, and we listed all the papers on trends. I mean, long-term trends, more than 5-6 years to some to 50 years. And for 80-90% of the papers, they don't show any trends, increasing amounts with the time. So it looks like remote areas like Antarctic, for instance, or remote islands very far from the coast are receiving more and more with the time. There is a real increase, but in fact, temperate waters and I mean, the closest part from the sources, the amount seems to be remaining at a constant level, and it's very strange. It has been increasing very fast until the 2000, but I mean, the general amounts are, I mean, all compartments, I mean, microplastics in deep sea or birds and so on, plastic litters in sea turtles, floating microplastics, sediment microplastics, beach on litter, and deep sea microplastics everywhere. So it's something like 25-30 papers indicating that there is no change for the last 10-20 years. So how do you link this kind of results with the models, and especially if you base your model with the increase in production? So it's true, I mean, because it has been measured, but I mean there's a gap there, and it's not really clear how the models may. Most of the paper published on predicted amounts, I mean increases from riverine inputs, for instance. There were 2 papers in Science in the last 2 months. The last one was 3 days ago by Borrell. They are all building on modeling. It's not the same kind of model because they are not oceanographic models, but it doesn't fit well with the results from most of the papers. What's the feeling of the modelers on that?
Can I just ask you something to clarify what your question was?
Yeah.
Are we talking about an increase in the trend, or are we talking about like the same trend going up, or
no,
like...
no. It's constant amounts of litter in most of the compartments of the marine environment, except remote areas where in most of them it's increasing. So I understand we can explain that with a kind of steady state situation with a long-term transport to areas where there is no input, just to balance. But I mean, what is very strange is that most of the published papers, it's something like more than 30 papers, we remain at constant levels of amounts. And when they are published with a appealing title like is still increasing, in fact, cumulative litter is increasing, okay, but I mean, the samples collected every year are remaining constant. And so there is a real question there. And the main question is how the models are building on that. So.
Maybe I try to answer. I think that you really put a challenge here for our work, because we have some uncertainty in terms of the scenario and the sources, and especially at time scale of 10 or 20 years or even more longer. We need also to find some estimates of good currents, even at such scale is not so easy.
Yeah.
And maybe the most important that we need to consider not only the surface, but to look at where plastic could sink or could go in the water column at the bottom. And this is a part which is not really too much investigated in most of the models, I think.
Yes, but it's really complex because even in the deep sea, I mean, they're not accumulating in most areas that were sampled until now. So I understand we may find some new accumulation areas such as gyres in the surface, at the surface. With the time, I mean, I don't know. But I mean, for now, in most of the areas worldwide, except remote areas, the levels are remaining at a constant level. Remain constant, yeah.
Yeah, it's really a challenge, I think. I think it's really a challenge, but we have a lot of different uncertainty to take into account.
Yeah.
François, do we have this data for plastic collected at sea, and could plastic accumulate on beaches, or it's clear it's not?
No, I mean you see OSPAR data, Mediterranean data in China too. They do have long-term monitoring studies, and the amounts remain constant all the time. And so there may be good reason, I understand that. But I mean, the fact is that OSPAR data, for instance, is to have started in the 2000, and for the last 20 years, there is no increase at all for more than 50 beaches. And so if there is increasing amount coming to the sea, normally we will see them increasing somewhere, unless degradation is fast enough to degrade them. Probably, I mean, it's not clear. I mean, the cycling is not clear for sure. And the question is more how the modelers may, I mean, consider this kind of information in the models. If you consider the inputs from the river, it's okay. I mean, no problem, because, but I'm not sure about regular monitoring on amounts. You see, for instance, the paper from Jenna Jambek saying that, or from Le Breton saying that, I mean, inputs from Yangtze was very high. When you discuss with Dao Jili, who is a specialist and working in Shanghai, he made some assessment there and didn't find so much. And so you see, there is really a gap there, and it's not clear how you may. I mean, there is one time where you will have to fit with real data anyway.
Yeah, for sure. Our expectation is toward this direction, of course, but I think that we are facing complexity in different parts, especially for the sources, because we know that the production is increasing. So especially, for example, we are looking at the moment on a project around the rivers in Indonesia. So even in a few years period, something like 5 to 6 years, when we put every year some particles, we see that the concentration along the coast or even at the ocean is still increasing. So it means that we have some difficulty with the sinks, and just from the surface at least. So it's probably a mix of different parts of different problems. But,
yes, I mean, the idea of, I mean, the plastic sinking, for instance, is probably wrong. Maybe part of it is sinking, why not? But if there is some, I mean, if there is a way for them to sink because of fouling, for instance, in fact, fouling will be grazed by animals, and then they will, I mean, they will come back to the surface. So it's probably more something like going down and back to the surface, moving in the midwater. But when you sample the midwater, there is not so much. So there are 2-3 papers, very recent papers, indicating they found a lot of microplastic in subsurface. It's okay. I mean, I trust the results, but many, I mean, we did try, for instance, with sediment sampling midwater, and we didn't find any for years, you know. And so it's really more complex than just saying that they will think, and then that's the reason that they are disappearing. Even if they are ingested by animals, for instance, they will be then excreted. And then it means that, I mean, they are coming back to the surface.
Yeah, I completely agree. It's really a complex problem. And this is a typical, some kind of problem that at least the problem can be established like that. We see no trends. But if we look at even some scenario where we put every year the same amount of particles, we do not see, we still see in our models some kind of increase.
Yeah.
So I think the problem is really on how we specify the things. And at the moment, we specify no thing at all. So, or at least we can just decide that after 10 or 20 years, they just disappear. Yeah. They're really not sufficient to do that.
There are some with increasing trends, but there are very few.
Yeah, very few. That's a real good question to challenge these observations.
Yeah,
okay, thanks.
If I can, from a authoritative point of view, the amount of plastic is not increasing, but we know that new plastics are seen.
We have some echo. Also, can you mute your microphone, please? René, go.
Okay, I think that François had a return of the sound. By new plastic, I mean plastic that were not in use before, like the masks that we have in a very, very large amount we have had for the last few months. And I've read in papers that they are found in great quantity in the ocean. So meaning that it's a rhetorical point of view. It's not a proof of anything. It's not because we don't see something that the thing doesn't exist, but new plastic arriving in the ocean are captured and seen as an increase in this category. So it means that there is a process that we don't understand, but that's not because that's the amount is not global, has not increased, that there is no more plastic coming to the ocean.
Exactly. Yes. I mean, you're right. But I mean, as a counterpart, you have some. I mean, the inputs may decrease in some places. I mean, there was some paper on that because of maritime transportation that has been decreased. There is less coming from ships also. So I mean, I understand it may be balanced. There will be some items that will be found more easily, and we did find some. There is not so much data in terms of real assessment for now, more the observation than quantification. But I'm okay with what you say, no problem with that. But when you see for the long term, I mean, it's not really clear, you know, how it works. Huh?
Yeah. Mm-hmm.
So basically, Francois, you're saying that the amount of plastic that arrives in the ocean right now is the same as a sink we cannot specify, correct? Or not? Okay, because we have not discussed the fact that microplastic then divides into fragments into nanoplastics. So maybe that could be a big sink, maybe.
So waiting for the response of Francois, I maybe make a comment on these two. I think that Francois was speaking about a study in the Atlantic Oceans where people from Brittany make a cruise, a cross section along the Atlantic Ocean and just estimate what's the concentration in the microplastics in the water column. And to answer a question to a journalist in France, I just tried to put the station that's been sampled by this team on our results. And I just said to this journalist that it could be a sub-estimation, I would say a low estimation of the concentration, because when you look at the station, it seems that they do not go on near the conversion zones, at least the core of the conversion zones where we can expect to have the more important concentration. So I can show, or I can send a figure to show that. François, you are there?
Maybe you can send the link of this study on the group chat.
All right.
If you have it, Andy.
I think, is this the, sorry to interrupt, somebody's got the microphone on with feedback. Is this the paper you're talking about that we published in Nature a few weeks ago?
Yeah, it's from the IMT cruise.
Yes, that's right. Yeah, that was my team.
That
work. So certainly that we took samples from within the center of the gyres, and then there was quite a lot of variation throughout the transect through the Atlantic. But I don't think it would be reasonable to conclude that we missed out on the accumulation zones. I think that's probably not the case. I mean, there were obviously shortcomings. We only had a dozen stations going down the Atlantic, all those sort of caveats. So I'm not saying it was a perfect.
My point was to say that it could be a low estimation of the amount, the total amount. If you consider that, if you look at all the stations and you say that we find at all the stations some concentration with the mixed layer and so on. But if you expect that you do not have some samples in this typical region of the core, maybe you just have a low estimation in terms of the total.
That would be even more concerning if it was a low estimate, because it was obviously much higher than other people's estimates.
Yeah.
Can I, whilst I've got the microphone on, can I ask Francois, I didn't quite understand why he thought that ingestion would cause material to come back up to the surface, which was at a lower level. But in general, I've worked quite a bit with defecation. It's a lovely subject to work on, particularly after lunch. It seems that even though fecal material does break down very quickly, the general trend is that when material enters organisms, they do sink. So I wasn't quite sure what I understood, Francois.
Yeah, well, I mean, the idea was to consider, I mean, marine organisms as sink for microplastics, I mean, having them ingested by different species and so on, and then, I mean, transported to the bottom, something like that. But the problem is that it has been published from different, I mean, by different authors, depending on the species. If you take, I mean, plankton, for instance, for 15 species studied by Cole from Exeter, it's about 2 or 3 hours before an ingested microplastics is excreted. And so it means there is no time to transport them to the bottom. And then if you look at mussels, oysters, I mean, bivalves in general, it's just 2-3 days. And if you take sea turtles from the rescue center that have ingested plastic before being injured and so on, they will excrete in about 2 weeks. So depending on the size, depending on the food and so on, I mean, they will never keep, and the question still remains for very small nanoparticles that may enter the tissue and accumulate, but for microplastic it's clear now that, I mean, they will be excreted, and most of them very quickly. And so it means that if they are ingested, normally they will be excreted very quickly, and it is not a way to sink, I mean, to the bottom. So maybe aggregates will be more efficient in terms of transportation to the bottom. But the idea was that if there is some fouling to make them more heavy, probably when sinking, there is not so much food in the bottom. Huh? And so any food anywhere will be of interest for grazer, for instance, and probably, I mean, the fouling will disappear, and then they may be able to float again to the surface. So this is the reason I was just explaining. It's probably more complex than just sinking directly to the bottom.
Yeah, I think you're right. Although clearly, when material enters fecal pellets, yeah, the general direction is downwards. But you're absolutely right that they don't last very long. They break up very quickly. But sometimes in sediment trap material, which I've worked on a lot, you find really quite a large amount of sediment material, fecal material in that. So it's. But
we didn't. We did find just one, and we lost it.
Yes, I mean sometimes, not always, but sometimes quite a lot of fecal material.
Okay, and then there was a scientist from Toulouse, a chemist. She was explaining that normally for the small particles, very small, the Archimedes strength is not enough to face, I mean, the resistance, the density of the water, so they cannot go to the surface. So it's a good, I mean, option, but it's just for very small particles. For larger, I mean, in the millimeter range and so on, normally they will go back to the surface, most of them. And also, especially because the density is increasing also to the bottom.
To sum up this very interesting discussion, does it mean that we have to go to the development of cycle life for plastics, for each type of polymer, for example?
For sure, this is the future, I mean, of understanding the cycle of plastics. I know there are some papers that were submitted recently about the links between the different compartments, between beach, floating, bottom, and so on. So that may come, but it's not modeled, I will say, just, I mean, descriptive at this stage. And I mean, for the years to come, there will be, I mean, a need to, I mean, quantitate, I mean, all the fluxes from one to a compartment, yeah, to another compartment, for sure.
Yeah, and it will be interesting because if we consider what we consider now is mesoscale, but if we go to sub-mesoscale, we will have some very increase of vertical velocity, for example, around some conversion zones. So it will change the dynamics also completely, I think.
But it's just a biogeochemical cycle, huh? To understand for each of the polymer, yeah?
Yeah, but if you go to a direction of cycle life, you have to consider with the different type of exchange along the water column. And at mesoscale, the story completely different in the model that at mesoscale or even climate change resolution.
But this is where models will be really important, huh? Cycling the plastic at sea. Huh?
Yeah.
I don't know if there is anyone from Eric Van Sebille's team in the audience, but I know that some people from Eric's team are actually working on the cycle you were describing, how plastic are biofoiled at the surface and then they sink and they're grazed on, or just the biofilm dies and falls out of the plastic and then goes back up, and they're trying to model this to incorporate into their global model of plastic at the Utrecht University.
No.
All right.
I think that they are all implied in a European kickoff program with Eric and so on. So I think.
Sorry, say it again.
They are implied in the kickoff for a new European program.
Okay.
Especially today.
All right. Do we have any more questions or comments on?
You meant involved. They are involved in.
Yes, they're involved. Yeah.
Okay. Okay.
Yes.
That was not okay.
It was a Frenchicized word. Yes.
And I just make my comment for the cruise of Richard, for example. It was with the idea also that maybe we have to consider for the future when we do some oceanographic cruises to consider modeling together and to try to develop a way where the model can put some light about the trajectory or at least some region that we want to sample before to go. So it could be a way to link also the modeling community with the in-situ observation.
Absolutely agree, Christophe. And in fact, modeling and observations should, in my mind, and I think with yours also, should always go hand in hand before and after the observations. So yeah. Absolutely agree.
That's because now we have some tools to make some kind of little prediction, or at least some kind of status of the conversion zones, for example, where we can expect to have more concentration or not. Or if you want, to sample a front, you have to make some sample before the front, after the front, and so on. So it's possible now with the tools from the satellite missions.
Yeah, and sampling is really something that, well, in my world, signal processing, which is difficult, and recently, I mean, over the last 10 years, we have been developing what we call smart sampling. That's sampling where there is something to look at. If you sample the people in Brittany, you find Breton more than people from Marseille. That's, well, it's an overstatement, but we have to be smart in order to assess that what we are sampling is representative of the whole trend and not a kind of a hole in where there is an accumulation and nothing outside. So, and I'm not criticizing anything. It's just a remark that went through my mind.
Yes, I totally agree that the model could be a useful tool to basically inform observers where to observe and where we can get the most of the observation, because we all know that we cannot observe the entire ocean with a resolution that will satisfy both the observers and the modelers. And definitely a lot of studies are to be done in this way. And the communities should communicate together in order to have these numbers, for sure. All right, should we want to have some concluding remarks from Thierry as well, maybe?
So we know some social people, or at least social sciences or economists and so on. So if anybody knows someone like that, we are interested. Okay, so maybe we can thank all the participants. Audrey, the last word is for you.
Sure. Well, Thank you everyone for listening and for the very interesting question that were asked, and of course to the three speakers who gave a great presentation and even greater answers to our questions. Feel free to send emails or go to the cafe sessions to further these discussions, and we'll probably see you virtually soon. And that's it, I think.
Is that cafe sessions with glasses of wine? Sorry.
Well, that's the thing, is like, since no one can see what's inside your mug, you can virtually put anything you want in there. Yes, see, René is definitely not drinking coffee at this time of the day.
It's always tea with me.
All right, should we close up this session?
Yes, maybe we can ask to Arthur to stop the recording and see you soon.
Okay, and just to the co-lead of the session, we would like to have a short report back of the best practices that could be involved with the topic that we were talking about. So because we have to report that on Friday, so we need them kind of a very, very short one page, one PowerPoint. No.
So you're asking this to the speakers or to the entire audience?
No. To the we call the co-lead of the session. That's Christophe, Thierry, and you.
Okay. All right.
It could be seen by everybody and also completed by anyone which want to make some points, I think, in notes, right, René?
Yeah.
Yeah, okay. So it's open to at least to everybody also.
For comments. All right. Thank you very much.
Okay. Thank you.
Thank you, Audrey.
And can I just do some advertisement for François Galgani, because he's going to be some co-founder of the Ocean Plastic webinars. And François will be our speaker in, I think, 8th of December at 11. So stay tuned for this. And if you don't know about the Ocean Plastic webinars, please feel free to Google it. You'll find us, you'll find our YouTube channel and Twitter account and all of these youngster things. And you'll find all the information on there. So yes, I'm happy to see you soon and talk to you soon, hopefully in real person.
Hopefully.
Hopefully sometime, yes.
Anyway,
right.
pin it down in your calendar, 8th of December.
8th of December, François will be describing all the international efforts around plastic pollution monitoring. And
the previous ones are still available on YouTube, right?
Of course, we've had 5 webinars yet, and we still have 5 to come, and of course more next year. So everything is available online.
Excellent. Thank you, Audrey.
All right, thank you, everyone.
Thanks a lot.
Bye.
Arthur, are you closing?
Yes, I'll clean up.
Okay.
Thank you, Arthur.
Thanks,
well,
Arthur.
thank you very much. That was a really, really lively and interesting discussion. So about the notes, just some brief statements on some key points in the discussions. If you could help with that, that would be great, and we can share them with all participants. Thanks.
Thank you. See you tomorrow.